Hello everyone, welcome to Electron Tech channel. In this video, we are going to watch a problem in FAR filter using Hamming window. Now the question is given. Here in this problem, we have to design a high pass filter. Frequency response is given and the frequency response is a desired frequency response. And the order of the filter, capital N is equal to 11. Our work is, we have to find the filter coefficient h of n and the transfer function h of z and the magnitude response we have to plot by using Hamming window. Now here you are seeing the functional representation. In the problem, this hd of e power j omega is the functional representation is given. So in this representation, modulus of omega is given. If modulus of omega is given, then the hd of e power j omega is equal to 1 for the omega value pi by 4 to pi and also from minus pi by 4 to minus pi. That is the meaning because modulus of omega is given. Now we can draw it graphically, graphical representation, so that the understanding will be better. Now you can see from pi by 4 to pi the magnitude is 1 and from minus pi to minus pi by 4 the magnitude is again 1. For the remaining values it is 0. As a first step, we have to find the desired filter coefficient function. But in this problem, we have been given the desired frequency response hd of e power j omega. Here the suffix small d that indicates that it is a desired one. Okay. Now we have to find hd of n. That is desired impulse response coefficient or Fourier coefficient, or we can call it as a filter coefficient. To get small hd of n, we have to apply inverse Fourier transform on capital hd of e power j omega. We have to find the desired filter coefficient. The formula is given. In the place of hd, capital hd of e power j omega, we have to substitute the values as given in the problem. From minus pi to minus pi by 4, capital hd of e power j omega is 1. Similarly, for the value of omega, pi by 4 to pi, capital hd of e power j omega is 1. For the remaining values of omega, it is 0. Now we have to integrate. For the integration, we can use the basic formula integral e power nx dx is equal to e power nx by n. Here the variable is omega because we are integrating with respect to omega. So the constant value we can take it as jn. Actually in the formula we are integrating with respect to dx x. So the constant is n, that is coming in the denominator e power nx by n. But here in our problem we are integrating with respect to omega. So omega is the variable here. So the constants are jn, that is coming in the denominator. Now we are taking the jn outside, okay, and then again we want to simplify it because the equation is in the form of e power j theta minus e power minus j theta. To convert this our equation in the form of sin theta, the 2j we have to move it inside so that we will get the new equation with sign. In the previous step, we got the desired filter coefficient function. Now we have to find the values for the desired filter coefficient. Here order of the filter is given as 11 and we can go for truncation because this is an FAR filter and it is symmetric. Now the range of small n we have to design now. Small n is given as capital N minus 1 by 2. So the maximum value is capital N minus 1 by 2. So let us see what is capital N minus 1 by 2. That is nothing but 11 minus 1 by 2, that is equal to 5. So the range of small n is from minus 5 to 5. Now for the first value n is equal to 0, we have to find the filter coefficient HD of 0. We have to take the HD of n equation in that equation in the place of n. We have to substitute 0. But if we substitute 0, what will happen is we will get the indeterminate form 0 by 0 because sin 0 is 0. We can use Elder's hospital rule. In our HD of 0, there are two terms. Similarly, there are two equations available in Elder's hospital rule. For the first, we can use the first formula, limit theta tends to 0, sin theta by theta is equal to 1. In our HD of 0, let's say this term is, first term is limit n tends to 0, sin n pi by n pi. Here this n pi, we can take it as theta. So for the first term, the answer. For the second term, Elder's hospital equation is limit theta tends to 0, sin n theta by theta. We have to compare this equation with our second term, sin n pi by 4 by n pi. So that 1 by 4 is nothing but n in our formula. In our formula it is n. So limit theta tends to 0, sin n theta by theta is equal to n. So for the second term, the answer is 1 by 4. Right. Similarly, we have to find n is equal to 1 to 5. But for n is equal to 1, directly you can substitute 1 in the place of n so that you can get HD of n. 1. HD of 1 and HD of minus 1 both are same because the filter is a symmetric filter. Similarly, we have to find HD of 2, HD of 3 and so on up to HD of 5. Now the third step is we have to find Hamming window sequence values. First, let's take the Hamming window sequence. That is given as W capital H of n. Capital H indicates that this is Hamming window. W indicates that it is a window function. Now in the place of capital N, we will substitute n is equal to 11. And then we can simplify it. Then we will get a simplified function. Here also, we have to find totally 6 values from 0 to 5. Window function is also symmetric. So, you find the value of window function for n is equal to 0, 1, 2, 3 up to 5. In the next step, we have to find the filter coefficients using Hamming window. The function is h of n is equal to hd of n, wh of n. The meaning is we have to multiply the desired filter coefficient into the window function. First, let us take n is equal to 0. Then you multiply hd of 0 and window function wh of 0. Similarly, you can get remaining 5 values. Now we have to find the transfer function h of z. The equation is given. In that equation, you substitute the values of n, small n from n is equal to 1 to 5. Then you can substitute the h of 0, h of 1 values. Then you can get h of z. Now, in the next step, we can find the transfer function of realizable filter. Actually, realizable filter transfer function is h dash of z. Z power minus 5 into h of z. We have to multiply z power minus 5 into h of z. The reason is in the previous transfer function, we got positive powers of z. So to convert the positive powers into negative powers, we have to multiply z power minus 5 with h of z. Here there are two equations, 1 and 2, that we have to compare it to get the filter coefficients for a casual filter. Our FIR filter is a casual filter. After comparing, we can get the 11 coefficients. Then, as a next step, we should find the frequency response. We got the filter coefficient. After that, we have to find the frequency response. Capital H of e power j omega. The formula is given. For that formula, coefficient is needed. Small a of n is the coefficient for a casual filter. A of 0 we have to find out separately. For that formula is given, and for the remaining value of n, the formula is given. Then from n is equal to 1 to 5, we have to substitute n is equal to 1, etc. up to 5. We have to find the different coefficient and we have to substitute in the h of e power j omega term. Finally, we should form a tabular column by varying the values of omega. Omega value may be varied in steps of 30 degree or some 25 degree. Starting value I have taken it as 0 and the ending value I have taken it as 180. Then we have to find the frequency response capital H of e power j omega and the decibel value also. After finding the decibel values, we have to find the log magnitude response. To draw the log magnitude response, our x-axis should be omega. Y-axis, we have to draw the decibel values of h of e power j omega. This is the last step. Thank you all.